Great. Yeah, so today we're going to be talking a little bit about generation algorithms. This will be sort of a tour through some of the most common methods, and we're going to talk a little bit about the theory behind them as well. If you're looking at the slides on the website, these might be ever so slightly different. But yeah, I'll try to stop at each section boundary for questions. Also, feel free to sort of interrupt at any point for clarifications. So we're starting off today with some great news. Let's say that you have some friend who maybe owns a giant tech company and they've gifted you this absolutely massive new Model M. It's a great model. It's pre-trained with the latest architecture. It's pre-trained on trillions of tokens of text. It's got 7 billion parameters. It looks like a really promising new model. You know, it's the top of all of these leaderboards. But if you actually take your new Model M and you sort of open up this box and kind of shake it out, maybe from last class, you know a little bit architecturally what this model might look like. But if you actually kind of take a closer look at it from a different angle, what you see is that M is actually just a conditional probability distribution. You put some input X into your model and you get some probability out for any given sequence that you're sort of interested in evaluating, right? And in particular, M gives you a probability distribution over all tokens in its vocabulary to predict like what token you would output next, right? And so this is what this equation says. Given some input X and everything that you've predicted so far, you get the probability of the next token Yj. And if you multiply this out over all the probabilities in your sequence, you can calculate the probability of any output Y given your input X. So what this like super fancy model that you spent a lot of money to train is really just a conditional probability distribution. But this turns out to be okay because you can use a conditional probability distribution to do sort of any task that we're really interested in NLP, pretty much any task, right? So by changing what you consider your input X and your output Y to be, you can get outputs from this model for things like translation, for summarization, for reasoning tasks, just by sort of changing what you consider your inputs and outputs in this setting. But there's sort of both good and bad things about your model being a probability distribution instead of just an oracle that gives you sort of a single answer for every input. One kind of nice thing about this distribution is that you can get at an idea of something like confidence, right? If you give your model the input 2 + 2 equals, and almost all of the probability mass is on the token 4, you can say like the model predicts with pretty high confidence that 2 + 2 = 4. Versus if you give it something that's maybe a little more open-ended, like you ask it to predict Graham's favorite color, and you see this distribution that's sort of a lot flatter, you know, the most likely output is green, but maybe we don't have a lot of confidence that that's the correct answer. This is really closely tied into the idea of calibration, which you guys talked about, I guess, a couple of classes ago now. The flip side of this, though, is that you notice that for this case, like 2 + 2 = 4, not all of the probability mass is on 4. And so models that are conditional probability distributions can hallucinate, right? Pretty much no matter what you do, there's going to be some non-zero probability to some output that's incorrect or undesirable, in some cases maybe even offensive, something that you don't want the model to output. And this is sort of an artifact of the way these models are trained. There's some great work kind of more on the theory side here that shows that this is actually true even if everything in your input training data is sort of correct and factual and doesn't have any errors, you'll still wind up with a situation where some non-zero probability mass is on some outputs that are undesirable or hallucinatory for sort of most inputs that you care about evaluating. So if we have these issues, how do we actually get a good output out of the model? And to do that, we're first going to talk about some sampling methods. But I want to pause here in case there are sort of any questions on this idea of a model as a conditional distribution. Great, so we can jump right in. So we have this model, right? We know at each step, at each token we might want to decode the distribution of likelihood over all vocabulary tokens, right? This conditional distribution we've been talking about for the next time step. And what we want out of this is a good output for some definition of good that we can sort of develop as we go here. So maybe the natural first thing to try is we have a probability distribution. Can we just sample from it, right? And this is something called ancestral sampling. So at each time step, we're going to draw a token from this distribution, sort of according to its relative probability, right? So if something has twice as much probability mass according to the model, we'll draw it twice as often. And we can sample from this distribution at each time step. And this is sort of a nice setup. We get exact samples from the model distribution. So using this setup, if you can you imagine like drawing an almost infinite number of samples, like a ridiculously large number, and you look at their probabilities, you sort of get something from this distribution with exactly the probability that the real model distribution is giving you. So this is great. This gives us an exact sample from the model. This seems to be exactly what we want. But you can guess probably by the fact that we're only like 10 minutes into class here that this is not really the end of the story. And there's actually a couple of problems with sampling directly from our model distribution. The one that we're really going to focus on first here is this idea of a long tail. So a model like Llama and maybe our new model M has 32,000 vocabulary tokens. And you can imagine maybe out of those tokens, there might be 1 or even 2,000 of those tokens that are sort of a reasonable next thing to predict for a really open-ended task, right? But there's going to be all kinds of things in that distribution that are maybe like punctuation. There may be tokens that won't actually lead to the correct answer. Like there's a lot of things in this distribution that would be all really low likelihood. And this is fine. These things just get low probability mass. But the problem is if you give sort of a small amount of probability mass to 30,000 different things, that mass will add up pretty quickly. And to see this, we have sort of this illustration here. I don't know if you can see the difference between the green and the yellow, but I've also drawn a little bar between them. This is a really long-tailed distribution, and the green part of the distribution, which is a lot of tokens with high likelihood, has 50% of the total probability. The yellow part, which is a lot of things that are all individually not super likely, is the other 50% of the probability. And so what that means is if you're doing something like ancestral sampling, 50% of the time you'll be sampling something really unlikely from this long tail. That seems sort of not like what we want, right? So is there anything we can do about this? And the obvious first solution here is, can we just cut off that tail? Like if we know these tokens are not super likely, can we just ignore them? And there's a couple of different ways to do that. The first of these is something called top K sampling, where we say, okay, maybe we think there are 10 reasonable like outputs-ish, right? Maybe we'll just sample from the 10 most probable tokens. Here, maybe we say if we want to pick top 6 sampling, we'll sample from just the 6 most probable tokens. And so in this example, you can see we originally had 10 tokens, and we're going to sample from just the blue ones, just the 6 most likely tokens. In this example, this distribution is pretty flat. There's a lot of things that are like kind of likely, right? So those 6 tokens are only 68% of the total probability mass. If we go like one time step further here, we might have a distribution that's a lot peakier. Most of the mass is on just a single token. And so sampling from just the top 6 tokens actually captures 99% of the probability mass. Maybe we say that seems a little excessive, right? We don't really need maybe all of these tokens that are all kind of low probability. Maybe we just want to sort of sample from the top half of our distribution or something, or the top 90%. So instead of choosing a top number of tokens to sample from, you could choose a top amount of probability. And this is something called top P or nucleus sampling. So P here is the amount of probability from your distribution you want to consider. So if you decide your P is about like 94% of the probability mass, you, in this first example here, would choose almost all of the tokens. You keep adding tokens in until you reach an amount of total probability that's about 0.94. But then when you get to the second step, where you have a couple of really highly probable tokens, you'd only need a couple of tokens to add up to 0.94, or even higher than 0.94. And so you would just sample from a smaller set of tokens. So in top K sampling, the total amount of probability you're sampling from can move around. In top P sampling, the total number of tokens you're sampling from might change. But maybe we sort of don't want to impose a strong constraint like we want like 94% here. Maybe just what we really care about is saying that we're not going to sample anything that's really, really unlikely, right? Another way of doing this is called epsilon sampling, where we just sample tokens that have at least some minimum amount of probability to them, right? So maybe we just want tokens that have probability of at least 0.05 here. In this first example, everything has at least some reasonable amount of probability, so we're actually going to sample from our full distribution. And then in the second example, when we have a lot of things that are really unlikely, we'll only sample from sort of the more likely part of the distribution. So all 3 of these methods are sort of different ways of trying to cut off the long tail using sort of different heuristics. The tail of the distribution, though, isn't the only thing we could choose to modify. We could also choose to modify this sort of peakiness of the distribution. So if you look here at the middle of these diagrams, say this is your original distribution over next tokens. And maybe you want to modify some properties of this distribution, like you'd say, I want an output that's really diverse and interesting and open-ended. Like maybe this is something like story generation, where you want to have sort of a lot of maybe surprising things in your output. You could say, I want to sort of distribute my probability mass more over the token space. And you can do this by sort of flattening this distribution, like you see on the right here, where now there's sort of more probability mass spread over this like wider set of tokens. You could also say the opposite, right? You could say, maybe I'm doing something like math where there shouldn't really be a lot of correct answers. There should be really only one, or maybe only like a few potential reasonable next answers. And so you can make your distribution peakier or sharper so that more of the probability mass is on the thing at the very top. The way you do this is you modify your lodges, your outputs of the last layer of the model before you apply softmax. So when you're predicting, you get your outputs of the last layer of the model, and then you apply softmax, which turns those outputs into a distribution, right? They all sum up. The like mass over all vocabulary tokens sums to 1. And so that is sort of a distribution you could sample from. If you divide those lodges by some number before you apply that softmax, you can make that distribution flatter by using a number greater than 1, or peakier by using a number less than 1. And this type of parameter is called temperature. You can apply this with any of the other methods for sort of cutting off the long tail, but what people will often do is just apply a temperature and then sample from that distribution. And that's what we call temperature sampling. So these, I think, most of you might already have been at least a little bit familiar with some of these methods. I want to touch briefly on a couple of other ideas for modifying this distribution, maybe some more complex and more recent ideas. And the one that I want to talk about in more detail is something called contrastive decoding. So the idea here is that we could incorporate some extra information at decoding time using some other distribution, some other data, or in this case, some other model. So if you've ever played around with a really relatively small language model, maybe something like GPT-2 small, you've probably noticed you try to give it some inputs and maybe it degenerates into just repeating the same sequence over and over. Maybe it gives you outputs that are just completely incorrect, like you ask it a factual question and it gets it wrong. And you don't see those problems if you look at sort of a larger model that's trained on more data. So the question here is, can you use what that smaller model is getting wrong to make your larger model even better? And the way we do this is by sort of the intuition that if the smaller model doesn't have a lot of probability on some answer, but the larger model does, it's likely because that larger model has learned something that the smaller model didn't know. And so here we modify the probability distribution coming out of the larger model to choose outputs that model thinks are very likely and the amateur or the weaker model thinks are not likely. So in this example here from their paper, if you have sort of a input like Barack Obama was born in Hawaii, he was born in blank, the smaller model would often do something like start repeating. And actually, if you sample sort of naively from the larger model, you can wind up in these situations as well, right? So if you just choose the most likely thing at each step, you wind up in this loop where it's like he was born in Hawaii, he was born in Hawaii, he was born in Hawaii. And this is behavior we generally don't want. If you do something like nucleus or top P sampling, you can wind up with things that are actually completely incorrect, like he was born in Washington, D.C. But if you use contrastive decoding, you take the outputs coming out of your expert model here, and you subtract out the probabilities coming out of the weaker model, and you can wind up with things that the stronger model ascribed probability to, but the weaker model did not, likely because these are sort of facts that the larger model knows that the smaller model does not. So here we actually get the year Barack Obama was born, which is maybe a fact that the larger model knows and the smaller model did not know. And so this is just one of sort of a broad class of methods where you can use external information to improve your decoding by modifying this distribution at each step. Those are sort of a brief tour of a couple of different sampling methods before we move into search. Yeah. Yeah.
Is it going to improve upon just relying on the expert?
Yeah, it generally does. And the intuition for why this might be, I think, is that there are sort of these degenerate cases, like just repeating over and over, that both the expert and the weak model would give relatively high probability to. Maybe the expert model is like slightly less likely to do these things, but it's still like sort of an easy case for the model to learn. And so both of those models will have high probability for those things. But the things that are genuinely like good outputs that only the expert would get right, those will have low probability under the weak model. And so you're sort of subtracting out all the degenerate behaviors and keeping only the really good outputs.
If you're generating a longer sequence with this contrastive decoding, how do you know which step you want to bring in the expert output?
Yeah, this is a great question. So for this particular case, oh yeah, sorry. So this was, if you're doing contrastive decoding over a really long sequence, like when do you choose to bring in the expert, right? And for contrastive decoding, we're actually going to do this at every individual time step. So we're going to use the expert model to decode, and we're going to bring in the amateur to sort of subtract out probabilities at each next token prediction. You don't have to do that. I think that's what they do in the paper. You could also decide to only do this sort of if you have high uncertainty or something, if you don't have a really sharp probability distribution. Yeah. Yeah, how weak should the weak predictor be? In the paper, what they're looking at is actually not a huge difference between the two models. So you can see here, this is GPT-2 XL and small. So there's a difference in parameter counts and like a bit of a difference in data, I think, here. But these are actually not like, GPT-2 XL is certainly not like a super strong model now. I think they try a couple of different settings, and the general intuition, I think if I'm remembering it correctly, is that you want a model that's not like so close in performance to your expert that you're basically just subtracting out useful things. But you also don't want a model that's like so degenerate that it is not, that hasn't learned anything useful about your task at all. So I think it might depend on what task you're looking at. Yes. This is for inference. So actually everything we look at today will not require any training of the model. Okay. Cool. So now we're going to step into sort of a slightly different set of strategies here, which is maybe we don't just want something from the model distribution or something from a modified distribution. Maybe we actually just want the quote unquote best thing, the single most likely output given our input, right? And here this would be the y-hat, the single sequence that satisfies, that has the highest score py given x for the x that we gave the model. This section is called mode seeking search because this is the mode of the distribution over outputs. If you sampled a huge number of times and you looked at the single most likely sequence you got, it would be this y-hat. And so how do we find this thing? Well, one idea is we know the distribution at each individual step. Can we just pick the most likely thing from that distribution? And so in greedy decoding, we take the argmax, the single highest probability token at each step, and we continue generating until the single highest probability token is the stop token, right? The end of sequence token. For an individual token, right? If we only want a single token output, this is exactly what we want. This is the single most likely output. And that's great. But if we're looking at something that is maybe several tokens long, are we actually going to get the highest probability thing? And if you kind of squint at this, you can see that maybe we have a problem here where the highest probability sequence that you get from multiplying across multiple steps doesn't necessarily start with the token that was highest probability at time step 1, right? Maybe if you're doing something like unconditional generation, the highest probability token at time step 1 is always the, but there could be a really probable sentence that just doesn't happen to start with the word the, and you would never find it using greedy decoding. So this isn't going to give us the highest probability output over a sequence that's more than one token long. Can we do anything better to try to find this output? And here we get into sort of one of the most popular decoding methods, the one that you've maybe heard of before, which is beam search. And the idea here is that we don't want to miss a high probability token that's hidden behind a lower probability prefix. So we want to kind of search through a couple of different options so that we don't discard something too early that might have high probability later on in generation. And this is a type of breadth first search. So we're going to look at a wide variety of options at a given time step, We're going to pick some set of them to continue, and then we're going to look at a wide variety of options for the next time step, instead of generating all the way through a sequence and then generating all the way through another sequence. And how this works is we're going to pick sort of a number of candidates we'd like to explore, a beam width. So in this example, we're going to pick 3, and we're going to say, all right, here are maybe 3 options for time step 1. For if we pick each of those 3 options, what would be the 3 most likely things for time step 2, right? Rather than choosing just the single most likely thing in greedy decoding, we're going to pick 3 options. And so now we have 3 options for time step 1, 3 options for time step 2. We now have 9 options here, right? 3 options and then 3 more for each of these. And we don't want to continue doing this because this is going to sort of combinatorially explode. So we need to choose some subset of these to continue with. And the way we do that is we look at the probability over this 2 token sequence, and we choose the 2 that have the highest probability overall. So in this instance, we've chosen sort of 1 thing from this first group and 2 things from the second group. And now we're back down to 3 hypotheses, each now 2 tokens long, and we'll continue generating to time step 3. We'll get 9 options, we'll prune it back down to 3, and we'll continue until the end of generation, where we now have 3 sequences, and we'll just pick the one that's highest probability out of those 3 to return. This is not guaranteed to get you the highest probability thing, right? You still have this risk that you could be sort of pruning out something that's high probability. But in general, this sort of works much better than greedy decoding. And this is, if you have a language model and you're sort of not sure what decoding method it's using, odds are pretty good it's either beam search or temperature sampling, right? This is very effective. This is used pretty broadly. There are, however, some issues with beam search. And one of the biggest ones is that when you're doing this maximum likelihood sampling, or the sampling to search for something that's very high likelihood, you really sacrifice a lot of diversity in your outputs. And in particular, you could wind up at the end of beam search with 3 different outputs to choose from that are all pretty much the same. Like, they're slightly different token sequences, but they look very similar. And so maybe you want to get sort of a more diverse set. There's a couple of different methods in this category. I'm going to very briefly shout out 2 of them. But the idea here is to sort of reintroduce some of the benefits of sampling while still doing this kind of search for high probability things. Diverse beam search is one of these methods. And here the idea is that we want to modify that scoring step when we choose which 3 out of our 9 beams we want to continue, to avoid choosing things that are really, really close to each other, right? So maybe our highest probability thing is some sequence A, and then if we look at the other sequences, there's one that's pretty high probability, but very similar to that sequence. And there's one that's like slightly lower probability, but very different. And so maybe we would choose a sequence that is a little lower probability to maximize diversity in our set, to try to get like sort of a wider range of options to choose from later in generation. So this modifies the scoring to not just take into account likelihood, but also similarity to other candidates. Another option down this path is stochastic beam search, where we're going to keep the scoring the same, but rather than choosing just the top 3 most likely tokens to expand out each beam, we're actually going to sample from some distribution. And you could sample from the model distribution directly using ancestral sampling, or you could use any of our sampling methods we talked about in the last section to do this. And the idea here is sort of similar to diverse beam search. We want to get sort of a wider exploration of our model's like output space. You know, we want to sort of explore more things instead of just winding up with a bunch of outputs that look very similar at the end of beam search. If folks are interested in these, I think these are both linked on the website. The papers that both of these ideas came from. Yes.
For stochastic beam search, the sampling probability takes into account the current path that you already traveled. Okay.
Yeah, exactly. So it's this like selection step here, but we're, instead of just doing greedy selection, we're going to do a sampling. Yes.
My question is on the contrastive.
Yeah.
Like, could you repeat for something super simple, like kind of thing? If both of them have a high probability, I would penalize them, like the slide of them.
Yeah, so you would, if it has a really high probability under both models, it would have a lower probability after doing this sort of contrastive decoding. Right. So if the smaller model is really good at your task, this might not work very well. Yeah, I think in the paper they're generally evaluating on these sort of like open-ended generation tasks. I bet this works a lot worse for now. Yes. Yeah.
Yeah, so maybe I missed it. Like, what do you mean by,
Yeah, this is a great question. And so the question is, how do we measure similar beams? You can sort of define any kind of similarity function you like here, anything that you'd use to evaluate like how similar something is to a gold reference, right? I think in the original diverse beam search, they do this by looking at like exact token match across the two, right? Like if these beams are the same in all but one of the tokens, or they have like, 50% of the tokens are shared across the beams, and maybe these are really similar and we should try to choose two things that are different. But you could swap that out for any metric you want. Yes.
So for the stochastic beam search, there's kind of like a shuffling that's happening at every concept.
For the stochastic beam search, there's like a shuffling. What do you mean by a shuffling?
So when it says modify the next token selection, is there like, is it searching at a different space and it's not searching within the same 3D tokens?
Is it searching in a different space? Yeah, so it's in the same probability distribution, but it'll see a different part of the distribution. So when you're doing the greedy search, you'll only ever look at the top 3 tokens in the next token distribution, because you're just selecting like the maximums. But in sampling, you could get the same tokens, right, if they're really high likelihood, but you could also sample something that's further down in the distribution. Yeah.
As a follow-up to that, like into our sampling, we're taking into account the probability of the prefix, like return hypothesis, right? Because otherwise it's the same as just ancestral sampling.
Yeah, so in the sampling, we're taking into account the prefix. Yeah, so we will take into account the prefix, but the sampling mechanism here could be ancestral sampling. The difference here is that we're also doing this sort of search step on top of that to choose the maximum likelihood things across multiple beams.
Another important thing is you sample without replacement. And so normally you sample with replacement and you might get exactly the same thing, but when you're doing stochastic beam search, you sample without replacement. So you get like 3 ones according to the probability, but they're guaranteed to be different.
Yeah.
Right. So beam search, like one of the characteristics of beam search is you always get 3 different things because you're picking the 3 top. When you do sampling, like stochastic beam search, you get 3 different things. They're not guaranteed to be the top. They could be distributed according to the probability distribution, but they're guaranteed to be different. So you can take a look at the paper for more details of exactly how it works, but that's important.
So then it's the main difference that compared to ancestral sampling that we have n options that we're keeping track of instead of going with only one.
And you can't sample the same thing.
Right.
Yeah, so just repeat for the recording, we've got n options we're keeping track of, and they're all going to be unique token sequences at least. You can actually get the same output sequence from 2 different token sequences if you tokenize slightly differently, but these will always be unique tokens. So that was sort of a set of methods that we've developed to try to find the most probable sequence out of the model. But in the next section here, we're going to sort of think about whether that's actually what we want to do at all. So what is do we really want the highest probability thing? We know that outputs with really low probability tend to be really much worse than outputs with high probability, right? Maybe I'm trying to predict like what the next sentence should be after the cat saw the dog, right? The cat sat down is way higher probability than the cat grew wings, and at least with the cats I've met, that sounds pretty much right? Like this is a much better output than the cat grew wings. But if you look at just the outputs with a relatively high probability, it's sort of less clear that this defines an exact ranking between those outputs, right? Is the cat sat down necessarily better than the cat ran away? These both seem like pretty reasonable outputs to me, even though one of them is slightly higher probability. And so do we really necessarily need to recover the cat sat down? And this gets a little more complicated still if we look at sort of a range of outputs. So say there's sort of 6 outputs that our model could give us. And here we're looking at sort of full sequences, not individual tokens, just for clarity. So maybe our outputs in order of probability are the cat sat down, it ran away, it sprinted off, it got out of there, it's very small, and it grew wings, right? So we're definitely sure that the cat sat down is a better output than the cat grew wings. And if we were doing a mode-seeking search, we would find that as our most likely thing if we do a good job searching, and we'd return that as our output. But if you look at the rest of this distribution, you see that there's actually a whole set of outputs after that that all say something that kind of means the cat left the area, right? It's just that this probability is split over these 3 different generations. And if you actually add up the probability mass of all 3 of these sequences, this is double the probability mass of the cat sat down. But because none of these individual sequences is higher probability, if you're doing mode-seeking search, you wouldn't be able to see this effect, right? So do we really want to return the cat sat down, or do we want to return something that means the cat left the area? The question then is, like, if it's not probability that makes an output good, what is it? So we have this one output that's really high probability, but it's very different from everything else in our set. And then we have a couple of outputs that are all pretty high probability and similar to a bunch of other relatively high probability things. So maybe it's sort of less risky to return one of these, right? Our thing that's higher probability but different than everything else could be different because it's way better, or it could be different because it's way worse. Another way to think about this is, maybe if you and your friends were cheating on a test, which you shouldn't do, but if you were going to do it and all of your friends sent you their answers, maybe one of your friends has a slightly higher score in the class than everyone else, but they said the answer was answer A and everyone else said the answer was B, right? You still might go with the answer that everyone else said because it sort of feels less risky. Like maybe everyone else got that answer. And so your one friend could be right when everyone else is wrong, or they could have made a mistake that no one else is making. So this is sort of the same concept, right? We want an output that's relatively high probability, but also relatively low risk. And so here, maybe if we were using this criteria, we'd return the cat ran away as our sort of single output. So how do you find something that's high probability and low risk? There's sort of 2 questions here, right? We have to figure out how to estimate probability. And if we're looking at a set of outputs like the 6 we saw before, maybe we can just do this by counting, right? We could sample everything from the model and get exact probability. Or we could take a sample from the model and just look at probabilities in that set. And from that sample, sort of one reasonable thing to do is just count frequency, right? If something's in our sample twice as often, we just say it's twice as frequent, or it's twice as probable. This is something called Monte Carlo sampling. If you do this enough times, like if you sample an infinite set, this would give you exactly the model distribution. But for the sort of reasonable size sets we're working with, maybe like 100 samples, this gives us a sort of reasonable approximation for what we need to do here at least. So we're just going to take a sample to get probability, and we're just going to count things in that sample to see how likely things are. That doesn't seem too bad. How do we estimate risk? The idea here is that we have a bunch of other things in this set of outputs, and we can treat those as sort of like pseudo-references, right? We can evaluate agreement between the thing we're looking at and each of those other references. And this is sort of the same idea as calculating similarity in diverse beam search. We're going to use some kind of metric to compare how similar these things are. This metric could be anything you use downstream. It could be like an n-gram overlap metric like rouge or blue, or it could also be something neural or semantic like something like BERT score or BART score. And so this concept is a type of decoding called minimum Bayes risk decoding. And what this equation captures is exactly the intuition that we were sort of talking about just a slide ago, where we're going to choose something that is low risk, which means it's similar to a lot of other things in this set of outputs we've sampled. And we're going to choose something that's relatively high probability, which means that sort of when we sum up over this, if something occurs in our set a bunch of times, it's going to have pretty strong weight in picking which of these outputs are similar, right? If sort of there's one thing in this set that appears a bunch of times, it's going to have a strong influence on which thing we pick. And so that kind of captures high probability in this setting. So to see how this works, we can look at an example in summarization. So we choose some metric, maybe we choose rouge, which is an n-gram overlap metric for summarization. And we say, we're gonna sample 100 things and we're gonna use this equation to choose the one that has the sort of lowest risk according to MBR. So if we do that and we look at this sort of table of results here, you can see that this outperforms the other sampling methods that we've looked at before. So greedy decoding here is just sampling the single most likely thing in each step. Beam search here is the BS with 5 or 10 beams, and DBS is the diverse beam search we were talking about. If we use minimum Bayes risk and we use Rouge as the sort of determiner of similarity, we do way better across all of our metrics, but we especially do really good at Rouge because that's sort of the metric that we've been using to evaluate. And then if we swap this out for other metrics, you still see a performance improvement over these search methods here. What's the sort of catch here? The catch here is that MBR requires you to sample 100 things. And so this is a lot more expensive. It's a lot slower at inference time. Yes. Yes.
Why does the beam search provide larger number of beams when loading?
It's a great question. Why does the beam search with more beams perform worse? This is a relatively well-known phenomena called the cursive beam search, which is...
You actually lost your mic, so I'll get you a new mic and you can speak up.
Okay, yeah, so this is called the cursive beam search. And the idea here is that beam search is like an approximate search, right? So if you add more beams, you should be doing better and better at finding the maximum likelihood thing. And generally you get something that is higher probability. But as you add more beams, you also often get something that does worse on your downstream metrics. Let's go back up there. Is that back online? Yeah. Is that back? Is that any louder? No.
Is it on?
Good question. Oh, there we go. Is that better? Great. Yeah, so why does this happen, right? Why do you get something that's higher likelihood but lower performance downstream? And this is like another sort of degeneracy of beam search, that this idea that the thing that is the absolute highest likelihood in your distribution might not actually be what you want downstream. This is sort of one of the other things that people use to motivate why you might want to do something like MBR instead. And there's a great paper about this problem called the inadequacy of the mode, because beam search is looking for the mode of the distribution.
One other thing I'd like to mention is it also goes together with how you train your models, because most of our models are trained using maximum likelihood. Maximum likelihood isn't explicitly maximizing our ability to get the best answer. It's explicitly maximizing our ability to estimate the distribution of answers. So if I say, if you said like, what is your favorite hobby or something like that? What is your favorite hobby in a dialogue system? Often it'll answer, I don't know, or something like that, because it like, you know, that's more likely than answering any specific hobby. Like it's more likely than answering basketball, bowling, you know, whatever else, because you have many, many different options. And so like, especially if it's something that's a little bit more complicated, it will avoid answering that. And in particular, it ends up answering very short things, for example, or sometimes it ends up repeating itself over and over again, or things like that. So it also goes together with like the training of the model as well.
Yeah, this is this is still a problem in modern systems. So if you actually look at the single, like if you could enumerate everything and see the single most likely sequence, it's often the empty sequence, just not outputting anything at all. And so if that's your true mode of the distribution, then doing better at mode seeking is not always like helpful. Yes. Could this be influenced by the confidence problem? Like, how so?
The mode seems to be more overrepresented compared to real distribution. So like coming up from might be
Right. I think I see what you're saying, which is that like the confidence, it gives you the confidence of like a single exact sequence, right? Not the like actual sort of semantic space of, and so yeah, if you look at just like if you look at just the probability scores, you get the probability of an exact string, when what you really actually care about with confidence is the probability of sort of like things that mean the same thing. Yeah, this is part of why like calibration is really hard for long sequences. Great. So we're going to touch sort of briefly on a couple of other things that aren't sort of always explicitly described in this framework, but that you can think of as variants of minimum Bayes risk. And if you're sort of interested in this analysis, I think as Graham mentioned earlier, Alex Z, who's a first-year MLT, and I wrote a paper about this, which you can check out if you're interested. So the two that I really want to touch on here are other sort of inference time things you can consider, which might look a little bit different on the first glance. The first of these is output ensembling. So say you have multiple different models and you get outputs from all of them, and now you need to choose a best output among that set. One of the sort of common ways to do this is to compare like an embedding similarity across models. Like, does model 1 think these two things are really similar? Does model 2 think these two things are really similar? And try to choose something that has really high similarity with a lot of other outputs. Of course, now that we've just recently been talking about MBR, you can probably see that this is the same general formulation, just rather than summing over a set of outputs from a single model, now you're looking at outputs over a whole set of models. So some types of ensembling fall into this category of minimum Bayes risk methods. Another thing in this category is a sort of recent decoding method called self-consistency. And the idea here is that you want to do something like mathematical reasoning, and you really care about getting the final answer right, but you don't necessarily care about getting all of the reasoning steps in between, right? So you prompt the model for an answer using something like chain of thought, right? You ask it to sort of talk through the steps it's going to do, and then give you a final answer. You sample many outputs using this, and then you completely throw away the chains of thought, and you just take the answer from each output. Once you have that set of answers, maybe you have like 20, 30, 100 answers, you just return the one that was most frequently generated. What this is doing is a type of MBR where the metric that you actually care about is exact match of this answer, right? Ignoring the rest of the generation. And so here we have sort of the same intuition that we want an output that is high probability, right? We're getting it generated a lot, but also low risk. Not a lot of the other outputs in our set disagree with this answer. So those are a couple of different variants of methods where we're sort of sampling a wide set of sequences and trying to choose the best one. MBR is one type of sort of sequence set re-ranking method. You could do other things to re-rank sets as well, but this is sort of one representative class of these models, or of these methods. Before we get into constrained generation, those are sort of the three broad categories of inference methods we'll discuss, which is sort of sampling from some distribution, searching over some space of distributions, and doing some kind of analysis over a set of samples to choose which one to return. Does anyone have any questions at this point? Yeah.
Yeah, so in the paper, you mentioned that average and model weights cannot be thought of as MBR.
Mm-hmm.
What is the thinking behind that?
Yeah, like why is averaging model weights not MBR? I think it's not MBR because the key thing that I think really makes a method MBR is this concept of comparing between multiple sort of pseudo references. And there you don't have the same, like you average model weights and you wind up with sort of a single output in the end that maybe is like using like information from these two model distributions that you've sort of smushed together. But it's not the same concept of like comparing against pseudo references or re-ranking in a set. Great. So now this is a wide variety of methods to try to find an output that's just sort of good, right? We want an output that is nice out of our model. But now we'd like to maybe impose a few additional constraints. So say I'm asking our model for some hobbies I could use to stay in shape. And no matter what, I don't want the model to recommend climbing. Like I don't want this as an option. I've tried it, I'm not a fan. How do I get the model to stop suggesting climbing to me? And if you sort of played around with some of the more recent LLMs, you'd say maybe this is easy, right? You just tell the model in the instruction that you don't want to talk about climbing. And having talked to Bard recently, I can tell you, unfortunately, that it's not that easy. So I tell the model I don't want to talk about climbing. It does okay for a little bit, and then it's like, all right, but maybe you want to try rock climbing. And so we could continue trying to instruction tune our model, but maybe there's sort of a way to impose this constraint on the decoding side instead. And so I'd say, all right, I'm going to do something dramatic, right? I know I can manipulate the probability distribution. I'm just going to set the probability of climbing to be 0. I don't want to see this token. Like I'm completely over it. And this is sort of nice in some sense because this is pretty easy to do. Remember, we're doing a softmax over the outputs to choose this probability distribution. And so if we add a huge negative number to the logic for climbing before we do this softmax, its probability is going to be basically 0, and we're never going to see it as an output. But this doesn't seem like a perfect solution, right? Because, what if the model recommends bouldering to me? Do I have to write like a sort of a list of every possible climbing synonym in the world? What if there's sort of an allowable way to use this token? Like I want the model to suggest hiking because climbing up a mountain to see a good view is relaxing. But that's a use of the word climbing, and we just said that we can't use the word climbing. Or what if we sort of generate other related terms before we get to the restricted term? Like the model starts suggesting maybe you can work out by going to an indoor rock blank. And then what are we going to say? We can't say rock climbing. So maybe the model suggests rock climbing or rock collecting is a hobby to stay in shape. And that doesn't sound good either. You could continue like sort of engineering more and more complicated rules here, but maybe we could do something that's a little simpler. So what if I just sample a bunch of outputs from the model and then I check if they're about climbing and I get rid of them if they are, right? This is sort of the advantage that it's pretty easy to check after the fact if the sequence has satisfied this constraint. We could train some smaller model to guess if the topic of a sentence is about climbing. We could check for keywords. We could have a friend who's willing to see this content, like filter through it and throw everything out that's not about climbing, that is about climbing. But if this model ascribes really high likelihood to this, like if this model was trained on, data from CS PhD students, this could be an extremely high likelihood suggestion. And so we might need to regenerate hundreds or thousands of sequences to find something that's not about climbing. And that feels a little bit inefficient, right? So is there something that we can do that's a little bit better than that? Well, really, we'd like to guess at some point during our generation if the sequence is going to be about climbing and maybe like recalibrate or, we could even restart or sort of shape our generation so that we don't wind up with a sequence that's about climbing in the first place. One of the methods that we'll discuss to do this is a method called fudge. And unfortunately, in their paper, they don't have the same anti-climbing bias I do. So this example is actually about formality instead. The idea here is that we want a sequence output of the model that is sort of satisfies this constraint of being formal. And the way we're going to do this is at each step of prediction, we get the outputs of what the model predicts is the next token, right? This sort of distribution here in blue. And we also have some second distribution, which says, given sort of what we have so far, how likely is this to be a formal sentence at the end, right? Does a sentence that starts, do you want, have a high likelihood of being formal versus a sentence that starts, do you prefer? And so this sort of guess at what will be formal at the end of the generation will put high likelihood on things that result in really formal sentences like, do you prefer or do you thus? Whereas the original model might have higher likelihood on things that are maybe more commonly said, like, do you want? So we combine these two distributions, you can just multiply them together, and then we sample from this modified distribution, which now has some sort of high weight on things that the model thinks are likely, but also takes into account the likelihood of satisfying a constraint. This is another sort of method of modifying our sampling distribution with some external information here. And so this results in sequences that wind up being sort of more likely to be formal, without having to sample a whole bunch of sentences and reject the ones that we think don't satisfy this constraint. So how do we get sort of a guess of what will be formal at the end of generation? This is where the name fudge comes from. The FUD stands for future discriminator. And so what they do is they train a model on prefixes to guess whether that sequence will be formal. You can do this if you have a bunch of data that's sort of sorted into formal and not formal, right? Every sort of prefix of a sentence in the formal category is a training example, right? You know, a sentence that starts, do you prefer? You can chop off each token to get sort of a set of prefixes to sequences that have the label formal, and you can do the same thing to your informal set and train a discriminator to choose between them, to say, like, what's the probability the sentence will belong to the formal set when we finish? And so this idea of sort of trying to guess at a given decoding step if we're going to wind up with our constraints satisfied at the end is a sort of key way to do constrained decoding, and one that we'll return to in just a couple slides. I want to touch on something slightly different, which is that maybe one of the constraints we care about is something a little more nebulous, like we want to match human preference. The way that we usually accomplish this constraint is a little bit different, right? This we usually do through like reinforcement learning through human feedback. And so we take sort of our original model distribution and we take a sort of really like tight like distribution of evidence that says like this model says that this sequence is really high reward, this sequence is really low reward, and we try to sort of combine them somehow through training. So we get a new model that is quote unquote aligned, and that it has like a higher likelihood of giving us things that have really high reward according to our reward distribution. You can view this though as a type of Bayesian inference. And so what this means is the distribution that we really want to get at the end is a distribution that combines our original model's distribution and some idea of like how likely we are to satisfy the reward, right? This we do through reinforcement learning, but if we sort of know what these two distributions look like, we've just been talking about a lot of methods that modify the original model's distribution with external information. It seems like maybe we could just add that external information in at decoding time to get some of the same effects. And it turns out you can do exactly this. So this is a paper from last year called Reward Augmented Decoding. And the idea here is sort of in the same conceptual class as fudge, but instead of predicting whether we're likely to satisfy the constraint, we're predicting how much reward we think that sequence will have at the end of generation. So we take our original model without doing any RLHF, and we get the output, we get the predictions for the next token, and then we use a model that's been trained to predict the likely reward given some prefix, like a future discriminator. And we calculate the likely reward if we pick each of those tokens. And then we use the combination of those two distributions to choose what to decode next. And this sort of gives you some of the benefits of RLHF without actually having to do reinforcement learning. So it's a way of treating, like, aligning the human feedback as just another constraint that you can impose at decoding. So those were sort of a subset of the constrained decoding strategies that people use. Before we get into human in the loop stuff, are there any questions on this? Yes.
So for the fudge one, like the red thing, do you have to train it for every specific constraint you want in the model, or is that also generated in the sample?
Right. So for the discriminator, do you need to train one for every constraint? And you do, yeah. So you need to have some set of data that satisfies your constraint and some set of data that doesn't before you can enforce a new constraint.
An alternative might be, like in the paper, that's what they did, but an alternative might be just to train a discriminator to determine whether any constraint was violated. So if you have 100 constraints, you could do a binary classifier about whether any constraint is violated, and then that would also be sufficient.
But if you wanted to add a new constraint, you'd still have to retrain.
You'd have to retrain or create a new model.
The reason that this is sort of relatively reasonable to do is that this determination of if a constraint is likely to be violated is sort of a a lighter weight or easier task to learn, you can use a relatively small model for this versus like your big model that just that has to be able to predict the next token for any sequence anywhere.
Yeah, another like interesting thing is if you think about it, normally you're predicting with your big softmax like this over all of your vocabulary. You can even use the same representations here to predict with a binary classifier whether the constraint is violated. Let's say you have 100 constraints. This is still a vector of size 100 compared to your vector of size 32,000 that you're using for llama, right? So it's not like this adds, the training would cost some time, but it adds very little like inference time, I guess. Basically.
Just a follow-up to that, like the rock climbing sounds good, right? So when you do the constraint, would you use like a more general word like the object of it? Like, do not suggest X or I guess like in that constraint for rock climbing, you can add like 20,000 values or like don't suggest really good things. Like, is there a way to generalize that with the constraint for like
Like, is there a way to generalize your constraint to be like, don't talk about this whole set of hobbies? You could do that by training a discriminator, by training one discriminator that considers all of those, or by training like 100 different discriminators, and then sort of taking like the maximum score from any of them, right? Like you want to be able to exclude all of these things, so you consider if any of them are violated. Yeah.
And for reward augmented decoding, how do we sort of like train that reward model, or does that just come from the previously done RLHF data that we stored somewhere, and then we sort of like train another discriminator, but this one now choose the word.
Yeah.
I do feel like fully understand.
Yeah. So how do we get the reward model here? We can use the same data that we use for RLHF, but we need a slightly different model. So for RLHF, we'll train a reward model over full sequences, right? And here we need to do the same trick where we sort of look at just prefixes and try to guess the reward downstream. But if we already have preference data, then we have some, like we have a data source to do this with. I think, if I'm remembering correctly, they also had a couple more sort of tricks for data augmentation to get this to work. This is sort of like a non-trivial thing to figure out, because like reward is generally a sequence level attribute. But.
And also, if you don't know very much about RLHF, we're going to cover that in the future class, so don't worry if this is
yeah, sorry to jump ahead a little.
No worries.
Yeah.
What's the key for real-world application of this? Like, why would we be doing this to ensure it could be like our LLM would want to highlight certain qualities, like we want our LLM to be more empathetic. Is it something along this line?
Yeah, like what are the real world applications? Like, could we use this to make an LLM more empathetic or something? Yeah, any real attribute that you can sort of collect like positive and negative data for, you could do this kind of constraint for. I think the ones you see most commonly are the human preference, and then like negative constraints, like you don't want your model to generate offensive content. And if you can build like a good discriminator for, is the sentence going in a really offensive direction, you can kind of stop it from generating. Yeah.
Would it be a good idea if you generate a bunch of content and ask the model itself whether it violates the constraint?
Yeah, you could do that for sure. Could you generate a bunch of samples and ask the model if it violates the constraint?
Yeah.
This is also a type of sort of sample and then re-rank strategy. But yeah, this would be sort of a more clever, like less heavyweight version of this, checking if it's about timings, right? You'd like ask the model if it violated the constraint, and if it's a good enough model, it could probably do that pretty well.
I suppose in that case you don't have to train anything.
Yeah, and this is sort of a general like the generating text that like satisfies a constraint is harder than checking if a text satisfies a constraint. So even if the model isn't good about like not generating text about climbing when you tell it to, it might be able to tell if text is about climbing. Yeah.
So how do you collect the data for this discriminator? So what I mean is that if you want to have different discriminators for different restrictions climbing versus hiking, then you have to collect that data for each one.
Yeah, like how do you collect the data to train this discriminator?
Yes.
Generally you're going to see like you'll look to see if there are data sets that already capture this attribute, or you could sort of write heuristics to try to recover it if it's an attribute that not a lot of other people care about. Like, you could write your heuristic to check if text is about timing, for instance, and then try to recover like noisy samples of data that is or is not about climbing. Or maybe you could scrape a climbing forum and then scrape like a hiking forum and use the difference between them. But for a lot of tasks, there's actually pretty good data sets already out there for this. So there's like, there's a lot of style transfer tasks that are like go from informal to formal, or go from this to that, or like make this text in an iambic pentameter, and you can find like data from those sources too.
We never like talked about fine tuning yet, but I'm really curious with like reward augmented decoding, whether it would perform better than like fine tuning on our other stuff. Like certainly more efficient. But I was just curious.
I think this is a comparison they make in their paper, but I don't remember what they're punched on. Yeah. In general, there's this sort of a like, you can pay a one-time kind of heavy cost to fine tune, or you can pay cost at inference time every time to make sort of to make your model better in any of these ways. And depending on how much inference you're planning to do, or like one or the other of these could be better. Great. So now we're going to talk about sort of methods for introducing human interaction into the decoding process. And everything we've looked at so far has been very sort of black box kind of hands-off, right? Like you give the model M some input, maybe we do some kind of manipulation on the decoding side, you get one output back, right? But in a lot of situations where maybe you have some high-risk application and you need somebody to be consistently monitoring and maybe intervening, or you're doing something where you want to do some kind of human AI collaboration, and you want to be able to go back and forth, or you want to have a conversation with the model. What you're actually doing is sort of a series of decodings with human intervention in between. And I'm going to talk about a couple of these strategies briefly. I think if you've used sort of a modern LLM, you're probably familiar with at least a few of them already. We'll sort of put names to each of them. And the set of examples that we're running with here are from a paper called WordCraft, which is about story generation with LLM assistance. But these can also be applied sort of more generally to any kind of task where you'd want to go back and forth with a model. The sort of easiest or maybe simplest place to start here is just with interleaving text, right? You can choose when the model starts and stops decoding, and you can choose when a human is writing text in between. And you can condition your model on sort of a mixture of human and model generated text to choose what to continue next. You can also do something like have the model generate a set of text, edit that text in some way. Maybe the human is imposing some really subtle constraint, like I want it to sound like my writing style. We don't have a discriminator for this, but the human can sort of modify the text and then continue generating from that point, and that will influence the style of the text that continues being generated. This case here is sort of you're writing a story together, and so you're going back and forth and editing the text like that. But you can also think of any kind of conversation with the model as the same kind of interleaving of text, right? The model gives some text, you provide some text, you go back and forth on like who's providing the text that conditions the model. You also might want to do things like more fine-grained replacement. So here the person has highlighted some text and said like, make this more descriptive, or shorten this to 2 words, or maybe you want some additional constraint like, can this be happier? Can this be sad? Like change the ending or something. You can accomplish this in a variety of ways. Here, this is done through input manipulation. So you prompt your model differently with different constraints. You can also do this with an actual modeling change. Like if you want some kind of infilling model, particularly for things like code, this can be helpful. So you want context from left and right sides. Or you can do this with the decoding changes that we talked about in the previous section, right? You could add a discriminator for descriptiveness of text, or you could do some kind of sampling and ranking method to recover a more descriptive output. Another thing that's very common in this space is sampling and re-ranking methods where the human is the one choosing what to return, right? So in WordCraft, you see a set of choices and you can choose which text to insert. But more commonly in something like ChatGPT or Bard, you see this little option to regenerate text, right? You as the human can reject the text and say like, no, I don't like this, give me a different output. And this is also sort of a way of controlling decoding just by doing it on a human rather than an algorithmic level. of course, you don't necessarily need a human in here. And so some recent work has looked at functionally using models to make these decisions instead. This is a prompting paper called Tree of Thought, which was sort of very popular on Twitter last summer. And the idea here is that you're going to generate several smaller sequences, like a couple of sentences, a reasoning step or a thought in the paper. And you're going to use a model to choose which ones to continue. And you can do different sort of constraints here, like I want to sort of rank this set of 3, or maybe I want to predict if anything in this set is wrong, like, is this a good reasoning step? And if the model says no, you no longer continue that. But the idea here is, through prompting, really achieving something that's sort of, if you squint at it, looks a lot like beam search, right? Instead of doing a like token level thing and making a decision based on likelihood, you're generating sort of several sentences at a time and making a decision based on this model's feedback, right? This signal from an external source, which here is a model, but could also be a human if you're willing to sort of wait around for them to make the decision. And so this is a way of sort of giving feedback on a broader level than single tokens to guide a decoding process to a final output. So the last couple of things we'll talk about here are sort of practical considerations, speed, choosing decoding methods, but I can take any questions before that too. Great. So how do you make this fast? And in particular, if you've ever tried to sort of benchmark performance of a model, what you realize pretty quickly is that the vast majority of time is actually spent in decoding. You have to generate one token at a time. You have to sort of pass that back through the model to get conditioning to generate the next token. And so this is generally fairly slow. This is sort of a major impediment if you're trying to do something like a streaming application where you want, or a chat application where you don't want the person to be waiting around for an answer. One way to do this is a method called speculative decoding. And this is a method where you're using a smaller model, not as like in contrastive decoding, right? We're using a smaller model to decide what not to generate. But here we're using a smaller model to decide what to generate. And the idea here is that most of these tokens are maybe not super hard to decide. It's just that occasionally the bigger model might want to go in a different direction. So these green tokens here are generated by a smaller model, or amateur model here. And the larger model acts largely as a verifier. And what it does is it checks if the output so far is going in a direction that's sort of in distribution for the big model, like something that's within the realm of what it might sample. And there's sort of an involved discussion in this paper of how you determine if something is in distribution. So here the smaller models generates like 5 or 6 tokens that the larger model says, okay, this looks great, until it hits a token that the larger model would not have generated in that circumstance. And then the larger model rejects that token and generates a different token instead. So you can see here, each of these red and then blue sections is where the larger model has rejected something and has to actually auto-regressively decode a single token. By contrast, if you were doing regular decoding, at each individual token in this sequence, the larger model would have had to make the full forward pass to decode a token. So here, rather than doing maybe, probably like 20-ish decoding steps to get this full sequence, the larger model has done about 8 decoding steps. And everything else is able to sort of verify a block of tokens at once. This sort of idea of like using a smaller model as an approximation is pretty powerful. And there's some great follow-up work on speculative decoding and sort of ways to do this faster or with stronger guarantees. But this general concept is, I would bet, probably how models like, part of how models like ChatGPT or BART are sort of generating text so quickly. There's another element here, which is like the model architecture being sparse, but I think that if you folks talk about mixture of experts, we might get into that later. How do you do this kind of fast inference? Libraries like VLLM will implement speculative decoding and implement sort of hardware level tricks, like choosing which attention weights to cache where to do faster inference. There's also great libraries for doing things like constrained decoding. So things like outlines will let you set constraints like I want my outputs to all be JSON, and it will impose additional constraints during decoding to ensure that that happens. And then pretty much anything in these first couple of sections we talked about, like sampling, mode seeking search, and sometimes MBR will also be implemented in pretty much any library you use for models, like Hugging Face, FairSeek, or JAX. So to kind of take a step back here as we get to the end of class, there's really two broad categories of methods that we talked about today. Given our initial distribution from the model for a next token, given our input, we can do two kind of different things. We can, at each individual decoding step, choose some kind of function to manipulate this distribution. And this could be something like like cutting off the long tail, like modifying the temperature, or adding external information from another model or from a discriminator model, right? Or we can, over a larger part of the decoding process, choose some function to choose between sequences. And this could be like choosing between next tokens in beam search when we're pruning beams. This could be choosing from full sequences when we're doing something like MBR or sample and re-rank methods. And you can do these two things in parallel, right? You can choose like a different function to manipulate the next token distribution, and then some sort of like broader thing to choose what you do with the full sequences you get out of that distribution. But there are sort of these two broad categories of decoding. So what should you take away from this? I think a couple of things. Decoding methods can be really powerful to control features of your output. If you want to impose particular constraints, if you want to factor in reward function or factor in a data source that you maybe didn't have at training time. And to some extent, you can do a more expensive decoding method to compensate for a worse model, or to compensate for a model that hasn't been trained to do exactly the thing you want it to do. Of course, you can't, use this to make GPT-2 small as good as GPT-4, but you can sort of, for some points in the middle, spend more computed inference time to pay for not spending as much computed training time. And particularly if you don't have access to the kind of giant GPUs you might need to continue fine-tuning your model, this can be a really powerful alternative. Yeah.
So say like you're building like something in production, right?
Mm-hmm.
Do people usually do sort of like that, add token inference before fine-tuning to see if it's gonna work at fine-tuning? Does that translate well?
Like try to see like if you have a model that you can do some kind of expensive decoding method for to get good outputs, is it then worth training that model?
Right.
There's some great recent work on like training models to produce the same kind of outputs you get out of MBR without actually doing the really expensive inference step. So at some level, like, yeah, you can decide like this model is good enough with this expensive method. We can try to make it cheaper by spending more money on fine-tuning. But it's not like necessarily guaranteed that that will be the case.
Okay.
The methods that we looked at have these sort of trade-offs in quality, in diversity, and in inference speed. So sampling from your model directly is pretty fast to do. You get really diverse outputs, but it tends to be lower quality. Whereas more restricted sampling, these sort of mode-seeking search methods, tend to be higher quality, but you get less diverse outputs. And that's why we have these methods like diverse and stochastic beam search to counteract this a bit. And then methods like MBR or other sample and re-rank methods tend to be very high quality outputs, but you pay for this with much slower inference time. But if I can kind of convince you of anything today, I think it would be this, which is that the decoding method you choose for your model has a really strong impact on performance downstream. You can get radically different results out of the same model without doing any additional training, just by choosing the different decoding method that you might want to try. And so when you sort of let your libraries pick a quote unquote like sensible default, you can leave a lot of performance on the table. So I encourage you folks that if you're deploying models in production, or if you're doing research, or maybe you look at your outputs and your model has some undesirable behaviors, to consider if the decoding method you're using is imposing some kind of intuition or some kind of inductive bias, and if you can alter that to get some of these behaviors without resorting to additional training. And that's sort of the end. I can take any other questions.
Yeah, I guess we don't have any questions. We can take questions up here. One thing I'd like to point out also is that I love the final thing that Amanda said here. Another thing is that my impression from dealing with things is that it's a lot easier to predict the effect of inference time, decoding time manipulations than it is to predict the effect of like fine tuning or something like this. Like, just to give an example, beam search with the maximum likelihood trained model tends to generate things that are shorter. Whereas greedy decoding tends to generate things that are longer and repeat more often and stuff like that. And if you try a few methods like this, you'll quickly find these kind of quirks of each of the methods. And so by forming a good intuition of this, you will also know how to fix these problems when you see them. It's like, oh, my model's repeating itself a lot. Maybe I shouldn't be using greedy search. I should be switching over to something else or something like that. So this is a good thing to know and play around with.
Yeah, and I think pretty underutilized too. A lot of folks will not think about a decoding method to fix their problem, even if like your model might actually be perfectly fine under a different decoding strategy.
Okay, thanks a lot, everyone. We can finish up.